All right, y'all. Welcome to my DP Chemistry curriculum, lesson 19, structure 1.5.1. This is where we're going to start talking about ideal gases. So, our guiding question is going to be, how does this model of ideal gas help us predict the behavior of real gases? And our starting with structure 1.5.1, we're going to discuss what actually an ideal gas is, how it consists of moving particles with negligible volume and no intermolecular forces. All collisions are considered elastic, and we'll be able to recognize key assumptions in this model. So that's kind of what this whole lesson is going to be. It's going to be some key assumptions as well as how to visualize ideal gases and how that will help us deal with gases in the future. So starting off, we have to talk about what the ideal gas model is. So it follows a couple assumptions. Now, you will have to know these. The IB sometimes will test you on these and ask you about certain ones, so it's good to just have them memorized, but they're a little bit common sense. So first off, we assume particles are in constant, random, straight line motion. So they're just kind of zipping all over the place. So if you have a container and you have some gas particles, you don't know where they're going, but they're always traveling in straight lines. And they're not going to be deflected. They can hit walls and bounce off them in other directions, but again, those collisions are random as well. So moving on to how they move in straight lines. Well, that's because the particles feel negligible forces of attraction between each other. Most particles do feel some form of attraction. If we have two water particles that are close to each other, they like to attract each other, which causes a problem because if we have two going in opposite directions, they will be deflected towards each other by feeling each other's force of attraction. But in an ideal gas, we say, no, this doesn't happen. They do not have any attraction. So we need to keep that assumption here. All right. The third one is particles collide with each other and walls of container, because our gases must be contained, in perfectly elastic collisions. What that means is if a particle hits something, like maybe the ground, it will come up to exactly the same level that it would before. No energy is lost. No energy lost. Now, this clearly doesn't happen. There's no way to lose no energy. There's always a loss of energy. But in an ideal gas, we assume no energy is lost, and it works pretty well for our circumstances. All right. The next one is distance between particles is so much greater than the size of the particles. Therefore, we consider the size slash volume of particles to be negligible. So we assume that the particles don't actually have volume themselves. The volume that we're actually counting is nothing. So let's see if I can somehow get a representation of this. I don't think my pen can go any lower. What it means is that the particles are so small that if we were to remove them, the volume is exactly the same because the volume of said particles is negligible, meaning we don't have to count it. It doesn't really contribute to anything. thing meaningfully. All right. The last assumption is average kinetic energy is directly proportional to temperature. What that basically means is that if temp is halved, the average kinetic energy of particles is also halved. We discussed this a little bit earlier in like lesson 5, I think, way back when. But basically, we're saying that temperature and kinetic energy are directly proportional. I have seen this as a question exactly as it is on a DP exam, where they said the temperature of a container of gas decreased by 1/2. What happens to the average kinetic energy of that gas? And the answer was it is halved. And it was wild. It was just 1 mark just to know that one assumption. All right. So, with that said, there are a couple influential factors. There are three influential factors to gases, and you should know this from our previous section when we discussed Avogadro's law of combining volumes. The three factors are volume measured in centimeters cubed or milliliters, or decimeters cubed or liters. I combine these because these are the same. These are equivalent. Decimeters cubed is a liter, centimeter cubed is a milliliter. The next one is temperature, which is measured in Kelvin. You're going to be measuring it in Kelvin, not Celsius. Please do not use Celsius. And then lastly, we have pressure. Pressure is going to be measured in pascals or kilopascals. And the thing about pressure, what you need to make sure to remember is this is the force of the particles hitting the wall of the container. Because pressure is force over an area. So if we have a container and we just look at one section of that container as particles bounce off it, we can define the pressure as the force over that area, the particles hitting that one section, the force of that over that area. So pressure is determined by the speed and quantity of particles hitting an area. Speed and quantity of particles hitting an area. All right. So this is all the stuff you need to know about ideal gases, and it seems like a lot, but you'll come to just think of it naturally as you think about gases. And when I think about gases, my favorite thing to think about is a classroom, an empty classroom full of blindfolded 4-year-olds. If you think about an empty classroom of blindfolded 4-year-olds when thinking about gases, you can start seeing a lot of these assumptions make sense. So these kids are given the instructions to run, and if they hit something, then turn around and run in a different direction. And so you imagine that these kids are just scooching around. They bump, bump, bump. They're kind of like the DVD symbol hitting different areas, and the kids are moving. Now, a couple things can happen. If you imagine the container gets smaller, actually, I can just do it here. Well, let me try and do this in a different way. If you imagine the container gets smaller, all of a sudden they are more likely to collide. So now that the walls of the container are so much smaller, this kid's going to collide more often, meaning the pressure is going to go up because pressure is the amount of collisions. Now, imagine the container got bigger. Oh, I lost my G, but that's okay. If the container now gets bigger, They're going to collide a lot less with things. And they may even collide with their other peers less. And because of that, we can assume that the pressure decreases. Now, we can also tell the kids to move faster. Moving faster is specifically a factor of kinetic energy because kinetic energy depends on velocity. If this kid now moves faster, if you tell all the little children in the room to now run really fast and they're just zooming around, they're going to collide a lot more. That also tells us the pressure is going to go up. If you tell them to move slower, they're going to collide a lot less because they're now moving slower. So when you think about gases, my go-to is just think about these children running blindfolded. They may collide into each other, they may collide into the walls. And depending on whether they're moving faster, slower, the place gets bigger or smaller, or hey, you might even drop another four kids in there. If you drop a couple more kids in there, you can take a wild guess what's going to happen to the number of collisions. It's probably going to go up because there's more obstacles. Meanwhile, if you remove all the kids but two, the collisions are going to decrease. So when thinking of gas, it's useful to think of small children running blindfolded. A couple of things I really love about that analogy too is if you think of them moving faster, when you run really fast, you get hot and sweaty because moving faster is an increase in temperature. And so you can start thinking about these proportionalities between kinetic energy and temperature. Moving faster generally makes you hotter and you get sweaty, while when it's really cold, you sometimes move slower. You can think of cold as moving slower because it is. And so I hope this analogy helps. I hope you get to understand your ideal gases. Otherwise, have a great day and see you all soon.